The goal in question 4 is to imagine a particle moving along a line. So we can imagine a particle and we know that it moves at different speeds. So it might go slowly at first and then pick up speed towards the end, or it could go start here and then, go fast and then slow. We don't know, but we know that the position is given by this function. So the first thing we want to do is to find the velocity at time t. So we know that velocity is defined as the change in position over the change in time, specifically the limit as change in time approaches zero. So we're sort of imagining this philosophical concept of instantaneous velocity. So the explanation for velocity becomes the derivative of the function. And so the derivative of a rational function is the bottom times the derivative of the top, which would be 5, minus the top, 5t, times the derivative of the bottom, which would be 2t, all divided by the bottom squared, t squared plus 9 squared. So when we do a little bit of distribution here, we get 5t squared plus 45 minus 10t squared divided by t squared plus 9 squared. So that equals negative 5t squared plus 45 divided by t squared plus 9 squared. So we know that the bottom, because it's a square, is always going to be positive. So we're kind of interested more in the top part, which is going to determine the sign of the velocity. So why do we care about the sign of the velocity? Well, let's just say that this is the function p of t, and or actually he calls it f of t. And so if this is time, maybe the function goes something like that. So we can imagine going back up to look at our thing here. Maybe it starts at 0 and then it goes to 5, and then, it starts going faster. So we're going to start off at, I actually had it faster, and then, yes, slower and then faster. So it might start off kind of slow and then suddenly go faster, and then maybe it's going to, go slow or fast. So the idea is we're looking at the change in this position. So maybe from, 0 to 2 seconds, it's going pretty slowly. And if we look at this, let's just make this even more obnoxious. There we go. So then from, this time to this time, it's going much faster because in a short amount of time, it jumped that far. Now notice though, what we're looking at the tangent, we can see that the tangent line here is positive. Here it's positive, right? Here it's extremely positive. So you can see that not only does the sign matter, but the value matters too. On the other hand, what happens as it's going backwards, as it goes down, right, the slope of the tangent becomes negative. So we've got negative here, and the slope of the tangent magnitude also shows you how fast that change in position is going as a respect to time. So given all that, we want to know, when is the particle at rest? Well, you can see from the drawing here, if the derivative is positive, it's going in one direction, right? And if the derivative is negative, it's going down in the negative direction. Well, it's just going away from back towards 0. So it would be at rest when the derivative is equal to 0, or when the slope of the line is equal to 0. So we're going to have negative 5t squared plus 45. And again, the bottom doesn't really matter because, as I said, it's always a positive, but we want that to be equal to 0. So if I just do 0 over 1, we can just cross multiply and say negative 5t squared plus 45 is equal to 0. So negative 5t squared is equal to negative 45. T squared is equal to 9. And so t is equal to plus or minus 3. Now remember that they said that t is greater than or equal to 0. So therefore, we're not thinking about t in the negative direction. So that means that when time is equal to 3, I think it was seconds, 3 seconds, the particle is at rest. Ooh. And again, we need to be sure that we understand the difference between at rest in the colloquial sense. I'm going to just take a rest and sit at this point for 15 seconds or 20 seconds versus the mathematical definition of rest, which means that the derivative is 0 and it might only be for that instantaneous second. So just a caution there. All right, so then the next question is, well, when is it going in one direction and when is it going in the other direction? So for that, we're going to go back to thinking about our graph up here and notice that again, what we're talking about in number 3 is when is the particle moving in the positive direction. So in this instance here, it's moving in the positive direction when the increase in the change in position is positive. So we want to look at the slope of the derivative, f prime of t. When is it greater than? And strictly greater than, because we had it equal to 0 here. So it's the same algebra, and except when we get to right here, we're going to get to negative 5 t squared is greater than negative 45. So now when I divide by negative 5, we need to change the direction of the inequality. So we're going to get t squared is less than 9. So t is less than 3. Again, only the positive in this case. So what they're saying here is that the derivative is positive when t is less than 3. So that would mean right about here. Okay, so it's going positive, 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 and then it goes negative, the derivative. So that would mean that in interval notation, remember that t is less than or equal to 0. So we're going to have an inclusive left bracket and only an open bracket on the right because t was equal to 3, it was at rest. Hope that helps.